In this section, we want to move into section 4.2 and talk about antiderivatives. So we learned what an antiderivative was in section 4.1, right? It was the function that is the solution to this integral. Okay, and this right here is our antiderivative. And what we want to see is how we're going to use them. This will begin to set this up that we're going to see that antiderivatives are going to help us find areas. Okay, so what exactly is going on here? So this goes back to one of the important topics of calculus. Suppose you wanted to find the area under some curve. So under some f of x between two values and above the x-axis. So let me illustrate what I mean by that. So you have this function. We'll just put it in the first quadrant. It doesn't have to be. And it might look like this. Okay, it can look like anything. So you want to find the area from A to B here, okay? This shaded area right here, where you can see the pen being shaded. So there's no geometric formula for this shape. So what you would do, or one way to find this area, is you can approximate it the area with rectangles. All right, and what you would do is you would take rectangles of equal width. Okay. Something like this. Did a little bit of a misdraw on that one there. And what you would do is you would find the area of each rectangle. Then you would sum all those areas. And then what would happen would be this sum would approximate the area under the curve. Okay, and so what I want to do in the next couple sections is formally, or in the next couple slides, is formally define this, work a couple examples, and show you where this leads. Okay. So these rectangles here, the sum of the areas of the rectangles are what we're going to refer to as Riemann sum. So we have this following figure from A to B. Okay. So here's A, x is equal to A. Here's x is equal to B. And what we wanted to do is we wanted to divide it into 4 subintervals, all right, each having width what we call delta x. Okay, so the width of these rectangles are all the same. Okay, so each rectangle, just to note that. And all you would do to find the width of the rectangle is you would take b minus a and then divide it by how many ever rectangles you wanted. Okay, so here we have 4 rectangles, but can actually be any number. And so hopefully kind of what you're seeing here, or what you're gonna see is that you know, the more rectangles you have, the more accurate your sum will be to approximating the area. Okay, so these widths are all the same, and so the heights of the rectangles, okay, will be determined at the function value for each of these x values. Okay. All right, so what you can see is, so the area here, this area for the first rectangle, it's going to be the width, delta x, times f of x1. And this area of this second rectangle here would be delta x, the width, times the height, which would be f of x2. And this would be delta x times f of x3, and so on. Delta x times f of x4. So the area of the rectangle of the curve is approximately the sum of the areas of these four rectangles. Okay, so as you see here, I wrote it backwards as delta x times, but you get the idea. And you can see here that this is not, the area of these rectangles is not like the exact area. It's just an approximation for it. Okay, like we're missing this area, but this one overestimates this area, overestimates, underestimates. It's like, it's a good approximation. Okay, so we denote this sum with summation or sigma notation, which uses the Greek capital letter sigma. So it just looks like this. So we're going to sum up f times x sub I times delta x. And this notation says I is equal 1 to 4. So it's saying increment I, start at 1 and go to 2, then to 3, then to 4. So it's just writing it in this notation here instead of out like this. Okay, so this is read as the sum of the product f of x sub I times delta x for I is equal to 1 to I equals 4. And so what this means is I takes on the values of 1, 2, 3, and 4. And you can see if you replace the I with first 1, then 2, then 3, then 4, you get the same thing. Okay. To recover the original expression, as I was saying, we substitute the numbers 1 through 4 successively for I in this f of x sub I delta x and write plus signs between the results. So it's just a summation. So like let's do an example here with approximating an area. Okay, so consider this graph. So we take this graph, f of x is equal to 600 times x minus x squared over the interval from 0 to 600. So what I want to do is I want to approximate the area by dividing the interval first into 6 subintervals and then 12 subintervals. Okay. And what I'm going to do is I'm going to really quickly work this through for you, just so you can see how this process is done. This isn't something that I would necessarily ask you on a homework, but just so you can just see how this is done. Okay, so the first thing is we need the width of each rectangle. Okay, so we divide the interval 0 to 600 into 6 intervals, or into 6 intervals, excuse me. So this is A, and this is B, in this formula back here. Okay. So you would take 600 minus 0 divided by 6. The width of each rectangle here would be 100. And what we're going to do is we're going to take x sub I ranging from x sub 1. We're going to start actually at 0. And x sub 6 is going to go to 500. Okay. So the 6th rectangle here. So like this is the first rectangle, first one here. This is the second, the third, the fourth, the 5th, and the 6th rectangle. Okay, you're going to notice that this first one here has no height. Okay, so that's going to be, there's no area for that one, and that's totally okay. Okay. So here's what you're going to do. Thus the area under the curve is approximately the following. Okay, so you're going to take in the summation I is equal 1 to 6. Okay, f of x sub I times delta x. So what I said was start at 0. Okay, so x sub 1 is equal to 0 right there. Then x sub 2 here would be equal to 200 and so on. So you take f of 0 times the width of 100 plus f of 100, because that's what the next one would be at 100 here, times 100, because the width always stays the same. And you keep going through that. And I won't bore you with the algebra here, but you know, like when you plug in 0 into the function, you get 0. When you plug 100 into the function, you get 50,000. Anyways, the total sum of this area here, we approximate the area to be 35 million. So it's the prox area under the curve. So if you do the same thing with 12 intervals, okay, the width will be 50. And again, you'll start at x sub 1 is equal to 0, and 12 intervals of size 50 gets you all the way out to 550. And you can see here the area is getting better approximated with more rectangles, right? Like look at this one here. You can see these huge gaps in the area and big overestimation. But when you get here with more rectangles, you can see that it's starting to get like a lot better. Anyways, if you go through this, you won't get the same area, right? You shouldn't, as you'd have different number of rectangles here. And we'll approximate the area this way here as 35,750,000. Okay, so what we're seeing here, Okay, the main takeaway, more rectangles are better. So then what's going to happen here is what we want to do then is theoretically fit an infinite number of rectangles there. So to fit an infinite number of rectangles in there, what you would do is you take the width of the rectangles. So you look at the limit as the limit of the width of those rectangles goes to 0. It gets smaller and smaller and smaller. So we're going to define this what we call the definite integral. Okay, so if you remember in section 4.1 we had the indefinite integral. So we're going to let y be equal to f of x be continuous and non-negative over some interval from a to b. A definite integral is the limit as, equivalently delta x goes to 0, of the Riemann sum of the areas of rectangles under the graph over a of b, over the interval from a to b. So what we're saying here is this. The exact area under the graph is the limit as delta x goes to 0, so this is the width of the rectangles. So the width of the rectangles goes to 0, okay? And obviously, you can't evaluate at 0, right? Because then, the width times the height here would just be 0. So you have to look at the limit process, right? And so we'll be able to evaluate this by what we call the definite integral. So notice it looks like the integral sign, but we have what we call bounds of integration. A and B are the bounds of integration. And what's going to happen is this definite integral here, I'm going to show you how to evaluate it, not formally in this section, in the next section, but this this definite integral, is going to give us the exact area. All right, so let me show you here. All right, and this is going to be using geometry. Okay. So let's find the value of the integral from 0 to 2. Okay, so here's the x-axis from 0 to 2. Okay, so this is my a, and this is my b. Of this function, 3x plus 2, okay, and then dx here. So we want to find the value of the definite integral from 0 to 2 of 3x plus 2 dx. So if you were to sketch the graph of this from 0 to 2, okay, you would just have this straight line here. All right, so what you want to see here is when you sketch this graph, you go, okay, does this have any geometric shape? And it absolutely does, right? This is a trapezoid, right? So here are the bases of the trapezoid, and this is the height of the trapezoid. So the height of the trapezoid is 2. The bases, this has length 2, and this goes from 2 to 8. This has length 8. So the area of the trapezoid, right, is the sum of the bases, so 2 plus 8 divided by 2 times 2. So this is 10 divided by 2 times 2. 10 divided by 2 is 5 times 2. This area under the curve is 10. So instead of writing what's the area under the curve between 0 and 2 of the function 3x plus 2, we would write it as the definite integral from 0 to 2. All right, let me show you 2 more examples of this, solving it geometrically, and then when we get to section 4.3, I'll show you how to do the calculus of this. All right, so let's find the exact value of these. Okay, so the integral from 0 to 5 of 5. So let's sketch this. So what this is saying is f of x is the function 5. So if you were to sketch this, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. You just have a horizontal line, right? And you want to go from 0 to 5. So you want to find this area here under the curve between these two values, between 0 and 5, and above the x-axis. Well, you just drew a square. So this area is equal to length times width, or side squared. So the side here, 5, 5, would just be 5 squared. It'd be 25. Let's try this one. The integral from 0 to 2 of 2x. So what you're going to have to do here, you're going to have to sketch the function f of x is equal to 2x. So 1, 2, 3, 4. So when you plug in 0, it's 0. When you plug in 1, you get 1 times 2 is 2. When you plug in 2, you get 2 times 2 is 4. So look at the shape that you just drew. You just drew the area under the curve between these two values. You just drew a triangle. So area is equal to 1/2 length times width, or like length times height, excuse me. Base times height. So it's 1/2, 2, and then the height is 4. So 1/2 times 2 is 1, times 4 gets me 4. So the exact value of this is 4. All right, class, you'll get a chance to practice this on your homework. And when you go to tackle these problems, okay, sketch this graph, this function, from this value here, from 0 to 2, and then find the area of the resulting shape. And then what I'm going to do when we get to section 4.3 is I'm going to show you, what's called the fundamental theorem of calculus and how to use calculus to evaluate this instead of sketching the geometric shape.